Hi, my name is Norain Maisara binti Ghazli and my metric number is 17206413. So today I will be discussing the question that been given to me during my final exam 1. But before we discuss the specific question that been given, I would like to discuss a little bit, give you an introduction about the general topic that have been given to me, which is Ralston method. What is Ralston method? Ralston method is a type of the second order Runge-Kutta method. RK2 method can be found into three methods, which are Huynh method, midpoint method, and Ralston method, which we will be discussing today. What is our general formula for RK2 is here, and Ralston method being given A2 is equal to 2/3. We substitute the formula here and we get A1 is equal to 1/3, P1 is equal to 3/4, and Q11 is equal to 3/4 also, and we have this formula here. So, Ralston method is actually, we consider the slope at a point 3/4 or 75% away from the previous point. K1 is the slope of point 0 and K2 is the slope of the point 75% away from the point 0. So we move to the specific question that been given to me, which is we need to solve an initial value problem of two ordinary differential equations by using Ralston method, and we need to allow the user to input the equation's variables, coefficient, and the solution are shown in a table and a graph. So for here, user enters the equations, variables, coefficient. I'm not sure how to do this. So I'm just use specific equation. Later on, we will discuss about this detail. Okay, so before we want to create the code for this, we need to find the exact solution so that we will know that our code is in the right way or not. We also can find the error. So at first we need to find the exact solution. So for example, I use this function, which is y prime is equal to 2x power of 4 plus y, and we get here is equal y is equal to negative 2x power of 4 minus 8x power of 3 and minus 24x power of 2 minus 48x minus 48 plus exponential of x times c. C here is constant. So this is our equation for exact solution. And then let's say if we want to find the value of c, we need to substitute the initial value problem. Let's say my initial value problem is x naught is equal to 0 and y naught is equal to 1. And then we get our constant is equal to 49. So we substitute it in here and we get my exact equation is here. And if you want to find y value at specific x value, we need to just substitute value of x that we want. For example, if we want x at equal to 1, then we just substitute in this equation and we get our exact value for y. Okay, so we get here exact value and we will compare it with our code. Later on, we will use the same IVP lah. Okay, this is for ODE2 because the question asks us to solve for the two ordinary differential equations. So we need to have two ordinary equation lah. And then I choose this equation to be my ODE2, which is y prime is equal to 3y plus sine x. Exact equation is y equal to negative cos x over 10 minus 3 sine x over 10 plus exponential of 3x times c. And if we also choose our initial value problem at x is equal to 0 and y is equal to 1, and then we get our c is equal to 11/10. and this is our specific exact equation. And if I want at x equal to 1, I will get our y value is equal to this one, 21.7876. We will compare it with our code later on. Okay, so let's move on to our coding in C++. Okay, this is my code. Okay, this is the equation. We need to solve an initial value problem of two ordinary differential equations by using Ralston method, and we need to allow the user enters the equations, variable, coefficients, and the solutions are shown in a table and a graph. We need to use the function program. Okay, first of all, like always, we need to include our header file, which is include iostream, include cmath iostream because we need to use cout, cin, include cmath because our function involve power, include iomanit because we need to use certain decimal places, include cst library, include stdio.h, include uni.std.h, which is the standard header file used in C programming that provide access to POSIX, which is Portable Operating System Interface. It means that you can use any type and declaration within it. We also include fstream because we need to involve file later on, and include string because we involve string later on, and like always we need to using namespace std, and we need to declare our function. So our first function here is here. We need to declare the type of this function, which is double f1 in bracket double x1 double y1. This is our parameter. We need to return our function, which is 2 times x1 power of 4 plus y1, and our second ordinary differential equation is been given here. We declare the type of it, which is double f2 in bracket double x2 comma double y2. We need to return 3 times y2 plus sine x2, and then we go to the main function. Okay, here. So int main, and then bracket we need to declare float x naught, y naught, xn, h, yn, k1, k2, k, y, xz, and c, integer I and n, and then we see out for ordinary differential equation 1, see out our differential equation, and then see out enter initial condition. We need to allow our user to enter any initial condition according to their needs, and then see out x naught, and then we see in x naught, see out y naught, see in y naught, see out enter calculation point xn. This means like which x do you want. This is like the stopping criterion. And then we see in xn, see out enter value of h, which is step size, and then we see in h, and then we need to calculate the number of iteration, which is the formula here is n is equal to xn minus x naught divided with h, and then we find the exact equation, which is given here. Based on our we find it manually just now, and then this is our we need to find our constant. We need to find by substitute the initial value problem here. As we know just now, our exact y equation is shown here. So if we want to find c value, and then we need to substitute with y naught and x naught, and then we get our c value, and then we redefine y exact, our y exact with xn, because here we want to find our y at our x. We see out fixed. This is to set our decimal places. See out fixed, see out the value of the exact y is equal to, and then we set our precision is equal to 5, which is our decimal places in 5 places, and then y exacts. Okay, this is we start to calculate our Ralston method, and here we see out this to make the table, because we need to show our solution in the table, and then we use for loop. I is equal to 0 until I is less than n, which is n we calculated here, and then I plus plus the increment, and then we write the formula for Ralston method. K1 is equal to F1 x naught y naught. K2 is equal to F1 x naught plus 3 times h divided by 4, and y naught plus 3 times K1 times h divided by 4. And then this is K is equal to double h. This is to substitute in our y formula. K is equal to double h times with K1 divided by 3 plus 2 times K2 divided by 3. And then we use to find the yn, we need to y naught plus k. Y naught is we get from here, and then we need to see out fix, which is we need to see out we need to set the decimal places. See out fix, see out this, set W10. This is to line up so that our table will look neat. And then set precision 5 x naught, set W10, set precision 5 y naught, set W10, set precision 5 yn. Okay, and then we use this is for our next iteration, which is x naught is equal to x naught plus h, and y naught is equal to yn. And then we display the result. See out value of y at x, xn is equal to yn for ordinary differential equation 1. And then we see out the absolute error. This is the absolute error. Exact value minus with approximate value. Exact value we obtain it from before, from here, and then we minus it, and then we abs, which this is floating absolute, y exact minus with yn. And then we see out this is just for the table. And then we call the GNU plot 1. This is our plot. Okay, so let's see our GNU plot. GNU plot 1. Okay, here is our GNU plot 1. This is a little bit different from we have learned before, because before this we learned to save it as PNG, but after I made some research, then I found this way we also can use GNU plot as GNU plot graph itself. No need to save it as PNG. And then we after that, this is the value, coordinate value for main function just now, because just now we substitute the value and we get the value in table, right? So we substitute the answer, the solution in here in set for x value 0, 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1.0. Actually this you can change lah. This value I get because I set x naught as equal to 0 and y naught is equal to 1 and h as 0 0.2. So my x value is 0 0.0, 0 0.0 plus 0 0.2, 0 0.2, and then 0 0.4, 0 0.6, 0 0.8, and 1.0. And here I stop at 1.0 because my xn is 1. I want to find my x until x equal to 1. And then my y values 1.0 because my y naught is equal to y 1.0, 1.22, 1.49, 1.85, 2.36, 3.17. This is from the table. Okay, and then we'll see it later. And then this is for y exact. This is y exact. We can use it. This is from the manual, and then we start our I is equal to 0, and we need to create and open our coordinate txt file, and then this is the format to create and open coordinate txt file times coordinate file is equal to f open in bracket coordinate.txt comma w, and this is to write the coordinate into coordinate txt file, and this we need to use for loop I is equal to 0 until I less than 6, increment of I, and then we fprintf coordinate file %1f and then x values, y values. Here in our txt file we ask it will appear our x values and y values, and then for I is equal to 0 and I is less than 6, increment of I, fprintf coordinate file, and then x values and y exact. Here we also the txt file also will appear x values and y exact values, and then we list the commands to run on gnuplot. Car, this we use the pointer cmds for gnuplot, and we set the title to be ordinary differential equation 1, set x label to be x, set y label to be y, and plot coordinate txt just now that we input in txt file, and use the 1, 2 with lines point. Here we can also use points, lines, and so on, anything. And then we open the gnuplot using pipe IPC. Pipe IPC is actually a technique for passing info from one program or process to another one. Okay, so file times gnuplot pipe is equal to p open gnuplot persist w. Execute, we execute the gnuplot commands one by one. Here our gnuplot commands here, we from I is equal to 0 and until I is less than 4, because we have 4 commands here, and increments of I, fprintf gnuplot pipe no plot pipe, and percentage of S, CMDS for no plot. We ask to print the command here. Okay, and then after that we also call the exact one here. This is what we learned before, which is we appear the solution in PNG format, which is in picture. So to open our nuplot.exe directory, we need to use this header file if def win32 const std string exe. We use string, so that's why our header file on top of this we need to include string. And then this is our where we want to where our new plot is located at, and then else const std string exe, and then this is new plot hash and if, and then we need to write the new plot commands into a file. That's why our header file just now we need to include f string const std string file name. We name our file name with exact1.txt, std of stream f file name dot c str f. This is our what we want in our plot. Set terminal png chiral, set output exact1.png. This is where we save the file name, which is here, and then we set key inside left top vertical right no reverse, enhance auto titles, box line type -1, line width 1.000. Our set samples 50, 50, and we plot it. This is our x range, and this is our function. Const std string cmd is equal to exe plus file name, and then to open our new plot to execute all the commands in exact1.txt, we need to write std system cmd.cstr. Okay, so we try to run for our first. So this is our first until here. This is for our first differential equation, which is here. This is for our first differential equation. Okay, so we try to run it for first, and we explain for the second function using our after we run it. Okay, so for ordinary differential equation 1, y prime is equal to 2x power of 4 plus y. We entered our initial condition, which is x naught is equal to 0, 1, 1, 0.2. Okay, so our exact value of y is equal to 3.19581, and this is our table. This is our initial value problem, and this is our initial value problem for y. So our y at x is equal to 1 is x is equal to 1. Our y value is equal to 3.17224. So our absolute error, we minus the exact value with the approximated value. This is our approximated value. our error is 0.02356. So this is for our second ordinary differential equation. The code is just the same like the first equation. We try to run it. For example, 0, 1, 1, 0.5. Okay, so we see it later. Okay, so we get our step size, our y-exact is equal to 21.78762, and this is our table. This is our solution shown in the table. And our y value for x is equal to 1 is equal to 14.09874 for ordinary differential equation 2, which is this. And our absolute error, which is exact value, this one, minus approximated value, this one, is equal to 7.68888. Our error is quite big because we use step size, we use low step size. We try to see our new plot. Okay, this is our new plot for first ordinary differential equation. Okay, we create the coordinate txt.txt file, so it will look like this. Will look like this because we use for loop for x values, y values, and x values, y exact. So from here, we read from the txt file just now, and then we form our new plot graph. Okay, this is our command. Okay, so here we see that for x is equal to 1, our y is equal to 1, which is, this is our initial value problem. For x is equal to 0.2, and 0.2, our y is equal to 1.22. Here we see it here, which is 3.17. 3.17 when x value is equal to 1.0, our y value is equal to 3.17, while our y exact is equal to 3.2. So from here we know that this is our approximated value, the below one, and the above is our exact value. And this is actually just the linear graph. So after we plot the GNU plot, we call the exact one, right? Okay, so we call the this is the GNU plot that we have downloaded, and GNU plot application that we have installed, and we save it here. And then this is command, which is we write it into our file and it appears here. Okay, so from our txt file here, we can form our graph like this. For negative 2 times x to the power of 4 minus 8 times x to the power of 3 minus 24 times x squared minus 48x minus 48 plus 49 times exponential of x. Okay, so for our second, it's done for our first differential equation 1, and then for our second ordinary differential equation, it's just the same code for just like the first one. We call the GNU plot 2. GNU plot 2 is here. Okay, we call the GNU plot 2, and this is our GNU plot 2. Okay, this is our GNU plot 2. Okay, so from here, we know that when x2 values equal to 1, y values is equal to 19.33 and y exact equal to 21.79. So it means that here the above one is the exact line, and the below is the approximated line, and this is just linear least regression, linear approximation. Okay, so for, and then we call for the exact 2. Okay, so from the exact 2, our commands will be saved in our txt file, and from our txt file we can form the graph here, which is negative cos x over 10 minus 3 times sine x over 10 plus 11 over 10 times exponential of 3 times x. Okay, so for the you can see from here that the difference between our GNU plot graph and our PNG. Our PNG is just simply like a picture, and actually I don't know how to plot the this is just for the exact equation. I plot just for the exact equation because I don't know how to plot the point. And then for GNU plot graph, we can see here, we can see the coordinate for every single point in the line, and we can also move it like this. Here we can move it. Okay. So that's the difference. We can compare the result using DAV, manually calculated, and Excel. So from DAV just now, this is our answer. For if we input the initial condition 0, 1, and we want to find x n is equal to 1, and our step size is equal to 0.2, and our x at 1, our y value is equal to 3.17224. And this is for equation 2. We get x is equal to 1, y is equal to 14.09874. And then this is our graph just now. We have discussed it just now. Okay. So, and then this is I calculated it manually, and this is just we need to find the first for the I is equal to 0, and we find it y1 is equal to 1.220135 when x1 is equal to 0.2, y2 is equal to 1.4928437, and while when x2 is equal to 0.4, this is just you substituted it in the formula given here. When y equal to 1 and x equal to 0. Okay, and then our answer here is equal to when x is equal to 1, our y is equal to 3.172243794. This is my manually calculated method, and this is for our second ODE. With just the same, using our initial value problem that we have substituted in our C++ just now. So we get the answer is equal to when x is equal to 1, y is equal to 14.09874097, and we also use Excel method. We just use this, and we get when x is equal to 1, y is equal to 3.17224, and I plot the graph using Excel also, and it looked the same like we plot GNU plot just now. And then this is for second ODE using Excel. When x is equal to 1, y is equal to 14.0987. So this is our graph. This is for exact and this is for approximated value. So from the tree method previously, we know that our answer is actually the same. It's actually the same for first ODE and the second ODE. So from here, we know that our method, our code from C++ is correct and our answer is also correct. So from my coding just now, I have mentioned two errors that I don't know how to solve it, which is I don't know how to let the user to enter the coefficient of the ordinary differential equation, and the second one, I don't know how to insert the points data into together with function in PNG format, but I solve it using GNU plot graph. But using PNG format, I found that one of the solution we need to have another file for the data like .dat, but I don't know how it works. Okay, for my first error, which is I don't know how to let the user to enter the equations variable coefficients, and then before this I use this kind of format. I let the user to enter the coefficient for Px and Qx because of our general equation for ODE is like this. So my function is like this, and this is for second function. I let the user to enter the coefficient for A and B, and my function is like this, and this is my main function, just the same like just now. And then I tried to run it. 1, 2, okay, as Px equal to, for example, I put 2 and it will ask me to input it again. So for example, if I input my first equation just now like this, so for y my coefficient is 1, so my coefficient for which is Px is equal to 1, and my Qx is equal to 2x to the power of 4. So it will come out like this, which is here is just the same answer. So I don't know how to fix this. So for my my correction for the GNU plot, second one, I found a way to solve it to use point together with the function, but here I use different function. Okay, so from here we get this, so it will come out like this. This is the point that we use. This is actually the same like my Z1 and Z2 here. Just the difference is here we define the fx and we set the x range -6 to 6, which is this for x-axis, and for y-axis -300 to 600, and for our first point, which is here, this is for the first point and this is for the second point, and this is the title here. Okay, so this is my correction for GNU plot, and here this is what it come out to our plot2.txt. So from here we can plot no plot just now. So this is another way also using DAT file, but I don't know how it works. We need to plot data first in the another file, and we use this. I think it's just it quite similar with just now. Okay, so and here I will put the link to my video later on. You can also do it for another function. You just change it here, and if you and after you get the answer, you can input the answer here. This is to plot it. And for the exact also, you can change the function here. And for the exact also, you need to find the exact value for another function that you want to find. For example, if I use the same function but with the different initial condition or different step size, 0.25 maybe, and my 1 is 1, and my xn I want to find at 1.5, and my step size is 0.25. Okay, then I get here, which is x at 1.5 equal what our y is equal to 7.34232. Okay, for my second ODE also the same. You can play around with the initial condition, step size, or your xn. And if you want to change the equation also, you can just change it. Okay, so that's all from me. Thank you.